Hello everyone. In this video, we're going to be covering concepts from the course of Chemistry 1412, also known as General Chemistry 2. So in this video, we'll be covering the concepts of free energy and equilibrium, with a couple other concepts thrown in there. The first concept we're covering is Gibbs free energy. Gibbs free energy, which is denoted with a capital G, combines the enthalpy and the entropy of a system. So it's going to be G equals H minus Ts, where T is our temperature. The free energy change, delta G, is a measure of the spontaneity of a process and of the useful energy available from it. So this will have the equation delta G equals delta H minus T delta S, where when our delta G is less than 0, we have a spontaneous process. If our delta G is greater than 0, we have a non-spontaneous process. If delta G equals 0, then our process is in equilibrium. And just as a reminder for some students, delta is going to be our final minus initials, or products minus reactants. So that's something very important to remember. In some instances, you'll actually have to solve for each of these variables, so delta S and delta H, in order to plug into the equation to be able to solve for delta G. And we should be going through a couple examples today so that you get a little bit more practice. Calculating delta G naught. Delta H of the system represents the change in enthalpy. T is our temperature, and delta S naught is the change in entropy. And that is going to be what each of these variables represent in our equation. So this is the equation that we had talked about before. Remember, the change is final minus initial, or product minus reactants. Delta G for the reaction can also be calculated using the values for the standard free energy of formation of the components. So this is going to be the delta G naught of our reaction equals the sum of our delta G naught products times their moles minus the sum of our reactants times their moles. It's a pretty similar process to what we do to find our delta S and our delta H. Now we're going to talk about the effect of temperature on reaction spontaneity. So we have the equation that we previously stated before, delta G equals delta H minus T delta S. The reaction is spontaneous at all temperatures if our delta H is less than 0 and our delta S is greater than 0, and our delta G is less than 0 for all temperatures. Those are the parameters for it to be spontaneous at all temperatures. The reaction is non-spontaneous at all temperatures if our delta H is greater than 0, our delta S is less than 0, and our delta G is greater than 0 at all temperatures. So let's go ahead and work through an example using the information that we covered in our previous slides. So hydrogen sulfide decomposes according to the following reaction, which is 2H2S gas yields 2H2 gas plus S2 gas. For this reaction at 298 Kelvin, delta S naught equals 78.1 joules per Kelvin, delta H naught equals 169.4 kilojoules, and delta G naught equals 146.1 kilojoules. What is the value of delta G naught in kilojoules at 900 degrees Kelvin? So we're changing our temperature and they want to know what our new value is. So let's go ahead and move over to our boogie board. So we know that our delta, or the equation that we need to use, is going to be delta G naught equals delta H naught minus T delta S naught. And they told us that our delta S naught is 78.1 joules per Kelvin. We know our temperature is going to be 900 Kelvin, and we know our delta H is 169.4 kilojoules. So we know our kelvins can end up getting canceled out, but our delta H and our delta S are in two different units. One is in joules, the other is in kilojoules. But because they want us to have our delta G in kilojoules, we can convert our delta S. So when you convert this from joules per Kelvin to kilojoules per Kelvin, we end up with 0.0781 kilojoules per Kelvin. And now we can actually plug everything into our equation. So we have delta G naught equals 169.4 minus 900 times 0.0781. And so when we multiply all of this out, we'll get a delta G naught of 99.1 kilojoules. And that is our answer. So make sure you're really paying attention to units, because by simply plugging it in with joules, you'll end up with a different answer. So make sure that you're paying attention to your units. So let's move back to our PowerPoint presentation. So here's the table that kind of explains what we had talked about before. So it tells you what your delta H, delta S, and delta G need to be at for your reaction to be either spontaneous at all temperatures, non-spontaneous at all temperatures, spontaneous at high or low temperatures, and non-spontaneous at high or low temperatures. So this is a very good chart to remember because some professors will provide it on your test and some will not. So if you want to know if your professor will provide it, simply send them an email, tell them this is the table from the book that we used in the spring of 2017. However, your book may have changed, so it might have a different table number. However, if you take a picture, I'm sure they'll know what table it is, and they'll let you know whether or not they are providing it, so you can determine if you have to remember it or if it will be provided for you. This is a condensed version of pretty much the previous table. However, in this table we have negative T delta S, and in this one I did not provide it. And so the way that you read it, it's saying when our delta H is less than 0 and our delta S is greater than 0, we have a spontaneous at all temperatures, which corresponds with delta G is less than 0. If we have delta H is greater than 0 and delta S is greater than 0, it tells us that we're spontaneous at high temperatures. If we have delta H is less than 0 and delta S is less than 0, we're spontaneous at low temperatures. And if we have delta H is greater than 0 and delta S is less than 0, we're non-spontaneous at all temperatures, and our delta G is greater than 0. So it's just a more condensed version of what we have talked about before. I did see it as a helpful tool, which is why I provided it for you. So let's do a checking of understanding. For a chemical reaction to be spontaneous at all temperatures, which of the following conditions must be met? So, for it to be spontaneous at all temperatures, we have to have a delta S greater than 0 and delta H less than 0. This is simply by looking at that previous chart and determining or remembering what is going to be spontaneous and what is non-spontaneous. And for delta S is greater than 0 and delta H is less than 0, it's going to be answer choice B. And this is an example concept type question that you could see on an exam. Let's go through another example. So they provided us with a reaction of NH4NO3 yields NH4 plus NO3 minus. They gave us our delta H's and our delta S's for each of the compounds. They want us to find the delta H naught, delta S naught, and delta G naught for each or for the reaction and determine if the reaction is spontaneous or if it's non-spontaneous. So it's a lot of work, but it's not too hard. So let's go to our boogie board to work this out. All right. So we had NH4NO3 yields NH4 plus NO3 minus, where our delta H is negative 365.56 for our NH4NO3. It is negative 132.51 for NH4 plus, and it is negative 205 for our NO3. Our delta S is 151.08, 113.4, and 146.4. And we'll use this information to be able to calculate the delta H naught, delta S naught, and delta G naught. So let's look at delta S first. So delta S naught and delta H naught, they're both going to be the product minus our reactants. So the first thing you have to do, ensure that your reaction is balanced. And this one's pretty simple, it's already balanced, so we don't have to do anything. But it's always better to check and be safe than be sorry and get the wrong answer. So our delta S equals our products, so 1, which is the moles, times, we're doing delta S, so 113.4, and we have 2 products, so plus 1 times 146.4, and that is our product, minus our reactants, which I'm going to write down here, which is 1 times, and it's going to be 151.08, and then we just simply have to condense from there. So you'll end up with delta S naught equals 259.8 for our products minus 151.08 for our reactants. So you subtract the 2, and your delta S naught is going to be 108.72, and that's joules per Kelvin. And now we can calculate our delta H. So it's the exact same process, but with the different numbers. So delta H equals 1 times negative 132.15 plus 1 times negative 205. That's our products minus our reactants, which is 1 times negative 365.56. And that's our reactants, because we only have 1 reactant. So our delta H naught equals negative 337.51 plus, because we have a negative here and we're subtracting it, so I just changed it to a positive. So plus 365.56. So our delta H naught will be 28.05 kilojoules. So we now have our delta S and our delta H, and we now need to solve for delta G. So I'm going to go ahead and erase this because we're not going to have enough room, and write out the equation for delta G. So delta G naught equals delta H naught minus T delta S naught, where our temperature was 25 degrees Celsius, which equals 298.15 Kelvin. So we now know our Kelvin, or our temperature. Our delta S naught is 108.72 joules per Kelvin, but we need to convert them so that our delta S and our delta H are in the same unit. So this is 0.1087 kilojoules per Kelvin, and then our delta H was 28.05 Kelvin. Sorry, not Kelvin, kilojoules. So we have each of our variables that we can plug in now. So let's go ahead and do that. We have delta G naught equals our H, so 28.05 minus our temperature, which is 298.15, times our delta S, which is 0.1087. So our delta G will end up with 28.05 minus 32.41. So delta G naught equals negative 4.41 kilojoules. So we now have our delta G. But that's not the end of our question. They also want to know if it's spontaneous or if it's non-spontaneous. So our delta G naught is less than 0, and we know that because of this negative. And when our delta G is less than 0, we have a spontaneous reaction. So we have our final answer right there. And let's go back to our PowerPoint presentation, where we're going to work at a third example. This one is pretty much the same, but it has an extra step. So we're now going to solve for delta H, delta S, and delta G. However, we want delta G at 25 degrees Celsius, and we want delta G at 500 degrees Celsius. So you're solving for two delta G's, a delta H, and a delta S. So let's go ahead and move over, and we'll just copy down the information they provided. So our reaction is N2 plus 3H2 yields 2NH3. Our delta H for N2 is 0. For H2, it's 0, and for NH3, it's negative 46.11. For delta S, it's 191.61, 130.68, and 192.45. So now we can start to solve for delta H and delta S. So let's do delta H. So delta H equals our product, so 2 times negative 46.11. And we only have one product, so that ends our first part. Minus our reactants, which is 1 mole times 0 plus 3 moles times 0. So anything times 0 is going to give you 0. So you're pretty much just solving for your products. So your delta H equals negative 92.22 kilojoules. And that's part 1 of your answer. For delta S, we're going to have 2 times 192.45 minus our reactant, so 1 times 191.61 plus 3 times 130.68. So delta S, you'll get 384.9 for your product minus 583.65. So delta S equals negative 198.75, and that's joules per Kelvin. But we know that when we plug it in, we need it in kilojoules, so we can go ahead and convert now. So this is going to be equal to negative 0.19875 kilojoules per Kelvin. So this is our answer. I'm going to go ahead and erase so that we can move on to our delta G's. So remember, we have 2 delta G's that we're solving for. And delta G naught equals delta H naught minus T delta S. The first temperature we're solving for is 25 degrees Celsius, which is 298.15 Kelvin. Our delta H is going to be negative 92.22 kilojoules, and our delta S is going to be negative 0.19875 kilojoules per Kelvin. So now we can plug it in and solve for our first delta G. So this I'll mark as part A. So delta G equals negative 92.22 kilojoules. You're going to go ahead and leave out the units because our kelvins will cancel that and we're left with kilojoules, which we've seen throughout the process. And we subtract our temperature, so 298.15 times our delta S, which is negative 0.19875. Okay, so this will condense down to delta G naught equals negative 92.22 plus 59.257. Because you're going to multiply these two, you'll get a negative. When you subtract a negative, it makes a positive. So our delta G naught at 25 degrees Celsius is going to be negative 32.96 kilojoules. And for this one, because our delta G is less than 0, we have a spontaneous reaction. And now we can do part B for our delta G. So delta G equals our delta H, which was negative 92.22, minus, this is where the change occurs. So we're no longer doing 25 degrees Celsius, we're doing 500 degrees Celsius. So 500 degrees Celsius is going to be 773.15 Kelvin times our delta S, so negative 0.19875. We can condense this, so our delta G equals negative 92.22 plus 153.66. So our delta G equals 61.44 kilojoules. We notice this one is positive. When our delta G is greater than 0, we have a non-spontaneous reaction. So this would be non-spontaneous. So it makes a big difference, your temperature. So by increasing our temperature from 25 to 500, it was a big jump, but it also changes from a spontaneous reaction to a non-spontaneous reaction. So hopefully these steps weren't too hard and they made sense to you. So now we're going to talk about delta G, equilibrium, and reaction direction. A reaction proceeds spontaneously to the right if our Q, which we covered back earlier in the beginning of the course, is less than our K, which we also covered. Remember, Q is reaction quotient and K is the equilibrium constant. If our Q divided by K is less than 1, so the ln of Q over K is less than 0, and our delta G is less than 0. So these are for the requirements for our reaction to proceed spontaneously to the right. A reaction will proceed spontaneously to the left if we follow the following conditions. So our Q is greater than K. If our Q over K is greater than 1, which means that our ln of Q over K is greater than 0, and our delta G is greater than 0. So moving spontaneously to the left means that it's a reverse reaction. So you can notice that everything in between here they're the exact opposite. So in a forward reaction, if we want it to occur spontaneously, we have to follow these conditions. And in a reverse reaction, if we want it to be spontaneous, we have to follow these conditions. If the reaction is at equilibrium, then our Q is going to be equal to our K. Our Q over K is equal to 1. So our ln of Q over K equals 0, and delta G also equals 0. Delta G, Q, and K. So we now have another equation. So it's delta G equals RT ln of Q over K, or RT ln Q minus RT ln K. So they both mean the same thing. They'll get you the same product. If Q and K are very different, delta G has a very large value, positive or negative. The reaction releases or absorbs a large amount of free energy. That is if they're very different numbers. If K and Q are nearly the same, our delta G has a very small value, whether it be positive or negative, and the reaction will release or absorb very little free energy. Delta G and the equilibrium constant. For standard conditions, Q is going to be equal to 1, which means that our delta G naught will be equal to negative R, which is a constant, T ln of K. The small change in delta G naught causes a large change in K due to the logarithmic relationship. As delta G becomes more positive, K will become smaller. When delta G becomes more negative, our K will become larger. To calculate delta G for any condition, we can use delta G equals delta G naught plus RT ln of Q. And so I'm going to show you a brief video that is going to go on this topic a little bit more in depth.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 71. It's on free energy and the equilibrium constant. For the last 20 videos, we've been talking about two things, thermodynamics and the importance of delta G, where we can think of delta G as the amount of free energy available in the products and the reactants, and a reaction occurring as we kind of move from reactants to products. And then we started talking about equilibrium and the importance of K, the measure of the concentration of products to reactants. As K is equal, so are the reactants and products. As it increases, we shift towards the right. As it decreases, we shift towards the left. But it's important that you understand that we can interchange these two things, delta G and K, and that they are inherently tied together. And so in any reaction, we can look at it using thermodynamic reasoning, and the importance of changes in free energy or changes in delta G, and also looking at it as an equilibrium reaction where we've got K, this equilibrium constant, which tells us are we shifting more towards the right or towards the left, and that there is a algebraic connection between these two, where delta G equals the negative RT, so that's going to be the gas constant times the absolute temperature times the natural log of K. And so we can interact between the two. And if we figure out our delta G, which, I mean, you could use the appendix in the back of most chemistry books to figure it out, that tells us a lot about what's going to happen to K. And so let's say K is equal to 1. We have an equal amount of reactants and products. Well, if we plug that into this reaction, that means our delta G, or a change in delta G, is going to be equal to 0. What happens if our K value is greater than 1? In other words, it's shifted towards the right. We now have a delta G that's going to be a negative value. So we think of this as an exothermic reaction. It's spontaneous. It's moving towards the right. And then if we look at a K value much less than 1, then we're going to get a delta G of a positive value. So that's an endothermic reaction. It's consuming energy. It's non-spontaneous. And so it's really tying together these two big thoughts that we've been talking about for a long time. Now, generally in AP Chemistry, we've only talked about exothermic or endothermic, but you should also understand there's energy involved in this. And so we could think of this as an exergonic or giving off energy reaction or an energonic reaction. Now, why is that important? Well, in biological systems, it's important to look at the amount of total energy that's either given off or being consumed, not necessarily the heat that's given off or consumed. And so if we look at this interaction right here between delta G and K, and let's look at a few reactions, reversible reactions. So in this one, the breakdown of water into its different ions, we would call a delta G value, if we measure that, of 79.9 kilojoules. Now let me show you what the K value is. It's going to be a really, really small value. What do we know about a positive delta G? That means it's an uphill reaction, non-spontaneous reaction. What do we know about a really small K value? That means it's going to be shifted more towards the left, or shifted more towards the reactants in this case. If we look at another reaction, in this case, we've got a delta G that's a negative value. What's that tell us about its K value? That's going to be a positive value. So this is a spontaneous reaction, or a downhill reaction, and in this case, it's shifted way towards the right. So you should be able to predict, if I give you a delta G, what's going to be my K value? Is it going to be positive or negative? That'd be the first question. And is it going to be a really small or a really large value? So since our delta G is a positive value, we know that our K value is going to be really, really small, just using this equation up here. And so you could plug in a gas constant and our absolute temperature, and that's going to be easily calculated. And so if we were to summarize it again, how are these two tied together? Delta G is negative, then we've got a K equal to a value greater than 1. That's going to favor the products, or it's going to move more towards the right. If it's equal to 0, K equals 1. And then if delta G is going to be a positive value, our K value is going to be much less than 1, or it's going to favor the reactants. And so why is this important? Well, if we're looking at biology, if we're looking at the chemistry of life, it really tells us how we can couple reactions together. And so if we look at this famous reaction up here, what we've got is glucose combining with oxygen, and we're making carbon dioxide and water. And so what is this? This is going to be cellular respiration. It's taking place in all the cells of your body right now. If we were to look it up in the appendices, we'd find our delta G value is going to be negative 2880 kilojoules. So we've got a delta G value that's a negative value. What does that mean? It's going to shift towards the right. So what would our K value be? It's going to be greater than 1. So that's going to favor our products. It's going to move towards the right. This is a spontaneous reaction if we can get it going, and we use enzymes inside the cells to do that. Now, what are we using that energy to do? Well, we've got another reaction here. We've got adenosine diphosphate, and if we add a phosphate to it, we make ATP. What do you use ATP to do? It's used in all the cells of your body. It's essentially cellular coinage that your cells use to do work. I mean, that's how you think, that's how you move, that's how you kind of do all the chemical reactions inside your body. And so what's going on inside our cells, more appropriately inside the mitochondria of our cells, is that we're coupling this exergonic reaction, or this reaction that gives off energy, with an endergonic reaction, one that consumes it. And so you could think of these as gears. As we're converting that sugar into carbon dioxide and water, we're using the energy that's released in that endergonic reaction, and we're tying that to, or exergonic reaction, we're tying it to an endergonic reaction. And so did you learn to relate delta G to K? In other words, what happens as we decrease our delta G? As we shift it more towards the right, what happens to our K, and vice versa? I hope so. And not only do I hope that was helpful, this is the last video in this series, and so I hope the whole AP Chemistry series has been helpful. I hope you've been along with me, and thanks for watching.
All right, so that wraps up that video. Let's go ahead and go back to our PowerPoint presentation to finish out our concepts. So now we're going to actually work an example where we're trying to use those equations that we had just seen, where either we're dealing with our K or our Q. For this example, we are going to find our Q. So a reaction has a delta G of 7.5 kilojoules, a delta G naught of 22 kilojoules, and a temperature of 30 degrees Celsius. Calculate the value of the reaction quotient Q under these conditions. So let's go ahead and move over to our boogie board so that we can do this. Because we know that we're dealing with delta G naught, and Q, we have to use the equation delta G equals delta G naught plus RT ln of Q. But we're trying to find Q, so we can go ahead and rearrange some of the information we have to be able to isolate our Q, or get it as isolated as we can. So this can become delta G minus delta G naught equals RT ln of Q, which then can become delta G minus delta G naught divided by RT equals ln of Q. And we can keep it right there until we can get rid of our natural log. So we can go ahead and plug in the information that they provided. So we have our delta G, which is 7.5, minus our delta G naught, which was 22, and each of these needed to be converted from their current unit, which was in kilojoules. So because I'm doing both, I'm just going to write it like this. Sorry, that's a 3. So this is just me doing the conversion. You can do them separately. It just makes sense because I had to convert both, so they're both times 10 to the third. Over our R, which is going to be 8.314, times our T, which is 303. And this is going to be equal to ln of Q. So when I do 7.5 minus 22 times 10 to the third, I'm going to get negative 14,500 divided by When I do 8.314 times 303, I'll get 2,519 equals ln of q. So when I divide these two, I get negative 5.7559 equals ln of q. And then I get rid of my natural log. So I say e to the negative 5.7559 equals q. So my q will be 3.16 times 10 to the negative 3. And this would be my final answer. So it's really manipulating the equations that I have, plugging it in, and solving for the variable I'm missing. And then finally, our last slide is going to be example 5. A reaction has a delta G of 4.3 kilojoules, a delta G naught of 18 kilojoules, so we'll have to convert these to joules, a temperature of 25 degrees Celsius, and they want us to calculate Q. So it's pretty much the exact same problem we did before, but with different variables. So we know we're using that same equation. So we delta G equals delta G naught plus RT ln of Q. And we'll go ahead and, just like before, we move everything over. One more step. And now we can just plug everything in. So our G was 4.3, our delta G naught was 18, and I'm converting them both over. And then our R is 8.314, has our temperature, which is 298.15, equals ln of Q. And I know I didn't explain it earlier. We had 25 degrees Celsius, but to plug it in, it has to be in Kelvin. So you convert whatever temperature you have in Celsius into Kelvin before you plug it in. So when I do 4.3 minus 18, and then times 10 to the third, I'll get negative 13,700 over 8.314 times 298.15 will give you 2,478.82. And that's going to be equal to ln of Q. So when I divide these two, I get negative 5.53 equals ln of Q. And then e to the negative 5.53 equals Q. So our Q is going to be equal to 3.97 times 10 to the negative 3. And that's pretty much how you will use this equation. So you look at the information they provide, you look at what you're actually trying to solve for, and you just adjust your equation to fit what you need. That's pretty much everything that we have for today. I do hope that this video was helpful to you. The link to the video you guys had watched is right here. He has some great videos on concepts related to this. Another great resource is Khan Academy, or you can always use your textbook. Other than that, thank you and have a great day.